On part 2, read all the information. We have an overall reaction. We have a delta H. It's negative, which means this is exothermic. Actually, that won't come into play here, so they're giving us more information than we need, just probably to see if some kid will try to use it. On A, we want the order with respect to each reactant. Now, what that really means is we want the exponent on the molarity of the reactants in the rate law. And it's really tempting to say, but I know the reactants. Look, there's a 2 there and there's a 1 there. But that's for an equilibrium reaction or an elementary step. This is going only to the right. And we don't have elementary steps. We have an overall reaction. This could have a bunch of intermediate elementary steps that we don't know about. And so we can't just guess the exponent from the coefficients. You must use the experimental data, which is why we had to go to all this trouble. So what we're looking for, though, is the exponent on the molarity. So let's see, it's going to be rate equals K times molarity of SO2 to some power in the box and O2 to some power. So the exponents are in the box. What's in the box? Well, we'll find out. Now, they wrote this out in a very thorough and, to my mind, very overly complicated way. Look, they wrote K over K, and that's going to cancel out. And they wrote the molarity of O2 twice, and that's going to cancel out. So really, what was the point? It's kind of a waste of time. And remember that this is a timed test in reality. They don't want you to finish. It's like the SAT, and that you are not supposed to finish like 1% or something of kids are going to finish, and it's purposely built that way. They want to spread out the scores, and to get a really good score, to get like 100% on this, you need to have this so nailed down it's kind of amazing. They expect you not to finish, so wasting time writing this out, to me, is just ridiculous. So let's do it a faster way. So the rate law will be these, right? Well, if I can eliminate this or this as the source of the change in the rate, then I can say, well, let's disregard it for a minute. And if I take line 1 versus line 3, the molarity of O2 doesn't change, and it can't be the source of the change of the rate. And of course, K is a constant and can never be the source. So that's why I think writing this is extra weird. So what we can do is compare line 1 to 2, and we can say, by what factor did the molarity of SO2 change? And it went from 0.1 to 0.3, and that is a factor of 3. So SO2 increased by a factor of 3. And it has some exponent box, and the rate increased by, and now it's really tempting to say, oh, we're going to do this divided by that, but remember, bigger is less negative. Bigger is less negative. If your teacher hasn't said something to that effect, I would write that down. Bigger is less negative, which means this is the bigger number, and we're going to do this one divided by that one. Plus, you might notice that this is increasing in the molarity, so it should increase the rate. It should be increasing this way. This is the bigger number. Grab a calculator, hit pause, and do this minus that, divided by that, and you get a number that is essentially 9. It's not dead on 9, but it's got just a tiny bit of experimental error in there. It's basically 9. So we have 3 to the unknown power caused a rate change of a factor of 9. What's in the box? Well, 2. 2 is in the box. So the exponent on the molarity of SO2 from the experimental data is 2. And one more time, not because of that 2. It's a coincidence. This 2 did not cause that 2, as you'll see in a moment when we do O2. So let's pick something here to figure out the exponent on O2, and the trick here is that we can't isolate SO2 because it never stops changing. That's fine because we know the exponent on SO2 and we don't have to isolate it. So let's pick something. They picked trial 1 and 2. And then we know that this increased by a factor of 2, and this increased by a factor of 2. But you know what? I wanted to show that you can even do it the other way. So I picked 1 versus 3. And I said, this increased by a factor of 3, and the exponent on it is 2, isn't it? It's 3 squared. How do I know that? Because I figured it out back here. The exponent on the molarity of SO2 is 2. It increased by a factor of 3, and the exponent is 2. Now, between there, O2 increased by a factor of 1. It did not change, which is a multiplier of 1. So this, remember there's a 2 there, times this is a factor of 1 to the unknown power. Remember, these are multiplied. creates a factor of, and remember we already did this math. This is a factor of 9 from here to here. So it created a factor of 9. So essentially 9 times 1 to the something power creates a factor of 9. So what's in the box? 0. Anything to the 0 power is 1, and which is what I needed. I need 9 times 1 equals 9. So the power is 0. So then they go and get extra picky and write this rate law, and they actually include the 0 power, which is kind of pointless, and they didn't do it in other places, I remember, so that proves the point. And so you can skip it because this is 1, and there's no point in multiplying by 1. On B, determine the value for the rate constant for K, and they're not going to say K, they're going to say rate constant, and they want you to know that that's K. By this time, we pretty much should know that. Now, what you can do is grab any line, and you can put in values here, and remember, we know the exponents, so we can put in values and the rate, and we can solve for K. Now, if we look at this, they used line 1 and put in a value of 0.1 here, and it gets squared, right? Because we discovered the exponent on here is 2. Well, I wanted to prove that I could use another line, so I used line 2 just to be ornery about it, and I said this is the rate equals K times 0.2 to the power of 2. Now, I'll tell you, be careful, because I misread it, and I got the wrong answer at first because I didn't put 0.2, and of course I got the wrong answer. Also, point out that there are a lot of decimals on this test, and it is really tempting to skip around and not be careful, and it's tempting to say that 0.2 squared is 0.4. And good job to all of you who just shouted in your mind, no, it's 0.04. Of course it is. So this divided by 0.04 gives you K. I will also point out that they are really sticklers about the units, and if you just put the number, forget it. You've wasted your time because you spent time on a problem that got you 0 out of 1 points. So also I'll point out, how do I know the unit? Well, the unit on this was molarity per second times K, and this is molarity. Remember, this is a molarity, and even the unit is squared, which means I get molarity per second over molarity squared, which cancels out to molarity times second on the bottom of the fraction. So I get the answer. Notice I got essentially the same answer, and the unit is per molarity second, which is the same thing as this. In case you never saw that before, then go back and have a discussion about that. But this unit is the same thing as this unit, so you can put either one. On C, we want the rate in experiment 4. Notice it says rate of disappearance. So they haven't changed anything. It's still the rate, and what we're doing is answering the whole here with the question mark. Experiment 4, right? Well, I just discovered K, and look, this is our rate law. We discovered the rate law, and we're discovering rate now, but I know K and I put it in. I know the value in number 4, it's 0.5, and it needs to be squared. And just punch that in the calculator and you get the rate. Don't forget the unit. On D, we're asked for the rate of appearance for SO3, and that's the product. And it says for experiment 2. Well, the rate of disappearance for SO2 in experiment 2 was this, and according to this balanced reaction, for every 2 that disappear here, you get 2 appearing there. In other words, it's the same amount. If you put in 100 of these, you get 100 of those. Now, my big advice, though, that I got in seminars on taking the test and so forth is do not just put the answer. They really hate that, and from what I understand, they will not give you credit. They want a mathematical piece of reasoning and not an answer that looks like you copied it from your neighbor. And by golly, you better have a unit too. So this person says, well, the rate of change from the SO3 versus time over time is the same as the other one. You know, maybe they would give credit for that, but personally, I would write it like this. I took the rate and I said, but there's 2 of these appearing for every 1 of those disappearing. Remember, it's back to stoichiometry and using a balanced reaction. And of course, the 2's cancel out and I get the same number. And I did not forget the unit. And I even put that in case they want that. E, you might be a little stumped if you don't give it some thought. There's no information on this paper that's going to tell you how to solve this. You have to know that if you want to speculate about another rate or another molarity that's not on the page, you're going to need the integrated rate law. It is supplied in the booklet. Turn back to the toward the front and find the pages. Now, also what they will not do though is tell you which rate law is which. So my little mnemonic is the one that uses LN is using number 1, and it is the first order graph or the first order integrated rate law. Which one do I need? And you know, I've used the first order integrated rate law so many times that I just started to think of using it anyway. But what's our rate law? It's a second order rate law. So the one with LN is the wrong one, and get the other one. Well, and then somebody says, but aren't there 3 because there's 0 order? It doesn't have an integrated rate law. There's no really such thing because the rate is constant. And we don't deal with third order reactions, so that's not a choice. So it's the one that corresponds really to the graph, isn't it? The graph that gives the straight line where it's the inverse of the molarities. So this one has the inverse of the molarities, and they would have written it more like this. And so we have the amount at the beginning times 0, or amount original, or A naught. I've heard many things, and AT, and of course A is just the amount being considered. So I already know K because I already figured that out back up there. And T, they told me, is 100 seconds. So there we know both of those. And the thing I missed the first time is it's experiment 1 because I couldn't find A naught, but it's experiment 1. So the beginning molarity of SO2 is 0.1. It's 0.1. And this will be AT, or the amount at the time that we want to talk about, at 100 seconds. At that point, just solve it. Multiply and remember to add this over, not subtract, and you get AT. Don't forget the unit. Should be molarity, right?